Hello everyone, we are going to learn coset and some of its example. Coset. Suppose Z is a group and H is any subgroup of G. Let A be any element of G. Then the set HA is equal to H into A such that H belongs to the subgroup H is called a right coset of H in G generated by A. Similarly, the set AH is equal to A into H such that H belongs to H is called a left coset of H generated by A. Here HA and AH are subsets of G. If E is the identity element of G, then HE is equal to H is equal to EH, and therefore H itself is a left and right coset. Since H is a subgroup of G, therefore E will be an element of H. So, if HA is a right coset of H in G, then EA is an element of HA. Thus, A belongs to HA. That is, A is an element of right coset HA. Therefore, if HA is any right coset, then at least the element A must be an element of HA. Hence, no right coset be empty. That is, every right coset is non-empty. Similarly, A is an element of the left coset AH. So, no left coset can be empty. That is, every left coset is non-empty. If the group G is abelian, then we have AH is equal to HA for all H belongs to H. Therefore, the right coset HA will be equal to the corresponding left coset AH. That is, if group is abelian, then left coset and right cosets are equal. If the group G is non-abelian, then we may have AH either equal to HA or may not be equal to HA. That is, in case of non-abelian group, two right cosets, left cosets and right cosets may or may not be equal. Note, if the composition in the group G has been denoted additively, then the right coset of H in G generated by A is defined as H plus A is equal to H plus A is equal to H plus A such that H belongs to H. Similarly, left coset A plus H is equal to A plus H such that H belongs to H. Now, example 1. Let G be the additive group of integers. That is, G is a group under addition, binary operation addition. That is, G is equal to 0 plus minus 1 plus minus 2 plus minus 3. This is set of integers which forms a group under usual addition. In this case, 0 is the additive identity element. Let H be the subgroup of G obtained on multiplying each element of G by 5. Then H is equal to 5Z is equal to 0 plus minus 5 plus minus 10 plus minus 15. That is, if we multiply each element of G by 5, then we will get H is equal to multiple of 5. Since the group is abelian, any right coset will be equal to the corresponding left coset. Now we will form the right cosets of H in G. We have the identity element 0 belongs to G, and H is equal to H plus 0 is equal to minus 15, minus 10, minus 5, 0, 5, 10, 15 up to infinity. Again 1 is an element of G, and H plus 1 is equal to minus infinity to minus 14, minus 9, minus 4, 1, 6, 11, 16, etc. That is, H plus 1 are obtained by adding 1 with each elements of H. 2 belongs to G, and H plus 2 is equal to minus infinity to minus 13, minus 8, minus 3, 2, 7, 12, 17. That is, H plus 2 is obtained by adding 2 with each elements of H. Similarly, H plus 3 is equal to minus infinity to minus 12, minus 7, minus 2, 3, 8, 13, 18 up to infinity, and H plus 4 is equal to minus infinity to minus 11, minus 6, minus 3, 4, 9, 14, 19 up to infinity. That is, H plus 4 are H plus 4 is obtained by adding 4 with each elements of H. Here we see that right cosets H, H plus 1, H plus 2, H plus 3 and H plus 4 are all distinct, and moreover these are disjoint, that is, have no common element. We can see that here no elements are common in H, H plus 1, H plus 2, H plus 3 and H plus 4. Now 5 belongs to G, and H plus 5 is equal to minus 15, minus 10, minus 5, that is H. Again 6 belongs to G, and we have H plus 6 is equal to H plus 1. Similarly, the right coset H plus 7 coincides with H plus 2. The right coset H plus 8 coincides with H plus 3. The right coset H plus 9 coincides with H plus 4, and so on. Similarly, also you can see that H plus 7 is equal to H plus 2 is equal to H plus 12 is equal to H plus 17, etc. Thus, we get only 5 distinct right cosets, that is H, H plus 1, H plus 2, H plus 3 and H plus 4, and union of these cosets gives the whole group G, that is, G is equal to H union H plus 1, union H plus 2, union H plus 3 and union H plus 4. Here G is the union of all right cosets of H in G. No two right cosets have elements in common. Example 2. Example 2. Let G is equal to 1 minus 1 I minus I, that is, G is the 4/4 roots of unity. Then G is a group with respect to multiplication. Let H is equal to 1 and minus 1. Then H is a subgroup of G. Now I belongs to J, and H into HI is equal to H into I, such that H belongs to H. This is equal to 1 into I, comma minus 1 into I. This gives minus I. So right coset HI is equal to I, comma minus I. Also minus I belongs to G, and H into right coset of H generated by minus I is H into minus I is equal to H into minus I, such that H belongs to H is equal to 1 into minus I, comma minus 1 into minus I. This is I minus I, which is also equal to hi. Since 1 comma minus 1 are elements of h, so write coset of h in 1, right? So h1 is equal to h into minus 1 is equal to h. Therefore, only two distinct and disjoint right cosets are h and hi. Since G is abelian group, G is also cyclic, so it is abelian group. So left coset of h in G is a right coset of h in G. Hence, right coset hi is equal to left coset ih, and right coset h minus I is equal to left coset minus ih. Thus, G is equal to h union hi is equal to 1 minus 1 I minus I. So, G is the union of two right cosets h and hi. Example 3. Let G be the group of all permutations of degree 3 on 3 symbols 1 to 3. That is, G is the group of all 1 1 onto functions on 3 symbols 1 2 3. Then the elements of G are the permutations f1 is equal to 1, that is identity function, f2 is equal to 1 2, that is image of 1 is 2 and image of 2 is 1 and image of 3 is 3, that is 1 goes to 2, 2 goes to 1. f3 is equal to 2 3, that is image of 2 is 3, image of 3 is 2 and image of 1 is 1, that is 2 goes to 3, 3 goes to 2, 1 goes to 1. f4 is equal to 1 3, f5 is equal to 1 2 3 and f6 is the permutation 1 3 2. Let h is equal to f1 f2. Let us form the right cosets of h in G. h f1 is equal to h, since f1 is the identity element of G. h f2 is equal to h, since f2 belongs to h. Now, right coset h f3 is equal to f1 composition f3 comma f2 composition f3. Because G is a group of permutations, so here binary operation is composition of functions. So hf3 is equal to f1 f3 comma f2 f3. Now f1 is the identity function, so f1 f3 gives f3 and f2 composition f3 gives f5. Because f2 f3 is equal to 1 2 2 3. Here image of 1 is 1 and here 1, image of 1 is 2, so 1 goes to 2. From right to left, we are going from right to left. Image of 2 is 3, from first image of 2 is 1, so image of 2 is 3 and from first image of 3 is 3. So 2 goes to 3 and 3 goes to 2 and 2 goes to 1, so 3 goes to 1. This is 1 to 3. This is equal to f5. Similarly, h f4 is equal to f1 composition f4 comma f2 f4 is equal to f4 f6. Here f2 f4 is equal to 1 2 composition 1 3, which gives 1 3 2. Since image of 1 is 3 and 1 goes to 3, 3 goes to 3. So image of 1 is 3, 2 goes to 2 and 2 goes to 1. So 2 goes to 1 and 3 goes to 2. So this is equal to 1 3 2, which is equal to f6. hf5 is equal to f1 f5 f2 f5 is equal to f5 f3 and hf6 is equal to f1 f6 f2 f6. and H(f)(6) is equal to F1(f)(6), F2(f)(6) is equal to F6(f)(4). Here H is equal to H(f)(1) is equal to H(f)(2), since F1 and F2 are elements of H. H(f)(3) is equal to H(f)(5) and H(f)(4) is equal to H(f)(6). Thus we get only three distinct right cosets, that is H, H(f)(3) and H(f)(4). So G is the union of the all right cosets of H, that is G is equal to H union H(f)(3) union H(f)(4). We can see that number of elements in each right coset is same as in H. The left coset F3H is equal to F3 composition F1 is equal comma F3 F2, which gives F3 F6. Here F3 F2 is equal to 2 3 composition 1 2. So 1 goes to 3, 2 goes to 1 and 3 goes to 2, which is 1 3 2 gives F6. Thus we see that F3H is not equal to H F3. So in every group, left cosets need not be equal to right coset. Here G is non-abelian group, so left coset is not equal to right coset.